In the previous video, we looked at the movement of this wave, both longitudinal and transverse, and we also learned how to define them. Now, in this second video, which is way more important in our study of physics and also being a science student, we're going to look at the stuff that we can measure. Because remember, in physics, if we can't measure, we don't study. So we're going to look at the stuff that we can measure that is related to the motion of this wave profile or wave particles. So, for example, we could measure certain distances, and since everything is moving, we could also measure the speed, and in order to measure speed, some form of time has to be measured as well. So in this video, we're going to define all of this, and let's go. Consider the good old water wave. I'm going to turn on the pipe now. And as usual, you can see the wave profile and energy transfer outwards in a circular wave pattern. But if we look from the side, we realize that this creates like a height of that wave, like your water level is changing levels, right? So I guess the first thing we can think about measuring, let me prop up my measuring tape here, is to actually measure how high is this water wave, like how high would it go, okay? So if you look at this knob here, where it says amplitude, if I decrease the amplitude, the wave looks more flat, the ripples are not as high. Whereas when I increase the amplitude, the ripples look much more higher. Okay, so what is amplitude? Well, amplitude is actually the maximum displacement of the water level. All right, and to show that in a graph, I'm going to draw the transverse wave or ask you to look at the transverse wave again. This is our good old transverse wave. Notice that there is a dotted line here. Okay, so all measurements should be taken from the dotted line or the equilibrium position. Now you might be asking me, Miss, what is the equilibrium position? Well, the equilibrium position here is just the position of this transverse wave if there is no wave. If there's no wave and the water is flat, that would be the equilibrium position. So we define amplitude as the maximum displacement of the particle from equilibrium position. So now we look at this particle. What is the highest possible position and the lowest possible position the particle can be? So for example, as we wait, if you look at this particle, is going higher and higher, higher and higher. This is the highest. So we will take that distance measured once again from that dotted line, or the lowest measured from that dotted line. So let's draw it on our notes. So here's a drawing of a transverse wave. And as you can see, if I want to label the amplitude or the maximum displacement, I'm just going to draw an arrow from the equilibrium position right up to this red dot. Let me use green for this. So here to here would be A. And of course, we could also take the bottom position. So here to here would be negative A. All right. So it's the distance measured from the equilibrium position. Let's write down the definition together. So oftentimes amplitude will have different symbols, okay? Sometimes they will use small a, sometimes they will use x naught, sometimes they will use capital A. So I'm sticking to capital A, okay? Because this one kind of makes sense, right? Large distance or displacement, okay? And as usual, since we are measuring a length, this one should have the base SI unit of meter, all right? And this would be defined as the maximum because we are taking the furthest position, the highest level of the water wave. So that would be the maximum displacement of, so we are taking a point on the wave, so there will be wave particle when measured from equilibrium position. Okay, so this definition for amplitude, the important key terms to include, it's the fact that this is the maximum displacement and it's the maximum displacement of a wave particle. Okay, and where do we measure that displacement from? Equilibrium position. All right, so if you look at the drawing that we have done just now, here, you will see that amplitude will be measured from the equilibrium position to the highest point or the lowest point. And it can be either in the positive or negative direction. This is for transverse wave. But how does amplitude look like for longitudinal wave? So if we look at this longitudinal wave, the orange particles, and I've mentioned before, we are taking this red color dot of rows of particles. And as you can see, this particle is actually oscillating, let me increase the frequency a bit so it looks a bit more less slower. So you can see that this one is just going to reach to a furthest distance to the right, pass by equilibrium, reach to the furthest distance to the left, pass by equilibrium again, and then reach to the furthest distance to the right. Maybe somewhere here. Pause. So I'm going to draw this now on OneNote. So this is a screenshot of the simulation that you saw just now. Once again, when we take amplitude, we will take from equilibrium position to where the particles are. Let's say if I measure towards the left, maybe this will be negative A. Okay, following regular sign convention. And towards the right, it would be positive A. So please understand that amplitude doesn't always have to be measured in the vertical direction. For transverse wave, yes, because the particle is moving up and down, so you measure your amplitude vertically. But for longitudinal wave, because the wave particles is moving left and right, so you should also measure your amplitude from left and right. That will be the first length that we can measure. The second length that we can measure is known as wavelength. Okay, so what is exactly a wavelength? Let us stare at this simulation for a bit. So if we think carefully about the term wavelength, which is length of the wave, what we are looking for is actually to measure how long will this wave be. So the intuitive thing to do is actually to take the maximum point and measure to another maximum point. Okay, so maybe we can take from here to here. Or we could also take from here to here. It would be the same distance. Okay, or we can take from this maximum to this maximum, or this maximum to this maximum. It could also be from this minimum to this minimum. Alright, so for transverse wave, it's pretty straightforward, and I'll label it now for you. So for transverse wave, if we are looking for wavelength, let's label the important points. This peak here is all known as crest, right? So I will call this C. This is C. So for one wavelength, we can measure from crest to crest. Here to here is lambda, wavelength. We can also measure from trough to trough. So I'm going to label this point as T and the other point here as T. And we can measure this distance as lambda. Okay, but how do we define this distance? Okay, we can say it is the distance between 2 points on a wave profile. All right, so this is wavelength, crest to crest, trough to trough. All right, but also at the same time, if you are thinking about longitudinal wave, what we are looking for is repeating patterns, right? So you can see pretty clearly that there are regions of compression. So right now, this is a region of compression. Let me label them. Region of compression. This one is compression. So we can take this distance all the way to here. This will be our lambda. Okay, this is our lambda. Of course, you could also take rare fraction and rare fraction. So roughly in the middle of where the particles are far apart to roughly in the middle where the particles are far apart, this can also be a wavelength. Of course, you will notice that this is just merely an estimate unless you really measure and make sure you're taking the midpoint. Okay, so these are wavelengths. But actually, it's kind of hard to define it just based on the region of compression and rarefaction. Let me label first. This is rarefaction. Rarefaction. Okay, so it's kind of difficult to define it this way. So the way wavelength is being defined is actually pretty specific. So in order to properly understand what wavelength is, we are going to look at this simulation. Notice that the distance between particle A and particle B is exactly one wavelength, one lambda. Now, before I start playing, I want you to look carefully at this particle and, is their distance changing? So meaning is the distance from particle B and particle A, are they moving further apart, closer together, or are they always the same? More or less, not more or less, are they always the same distance? Let's see. So I'll play the simulation now. And here you can see that they are sort of like moving down together, moving up together, but the horizontal distance between them are the same, right? So since their distance is 1 lambda, the distance between the horizontal distance between the red dot and the blue dot is 1 lambda. So it doesn't always have to be trough to trough, although currently it is. It can also be like from this equilibrium position to this equilibrium position, or it can be from crest to crest. And even if I randomly pause at some in-between point, like that, this red to this blue is still lambda. So what we are looking for is not really crest to crest, but it is the distance between two particles that are moving together. Okay, look at them. They always move together. They move up together. They move down together. And because this is such a special relationship, we actually call this in phase. Let me write it down for you. So the definition for wavelength, let me just put a symbol here for you. This would be lambda, defined, written in this symbol. Unit is still meter. Okay, and what lambda is the distance. So if you think about the simulation just now, it is the distance between two wave particles that are in phase. So in phase is a special term to define two wave particles that are moving together. Okay, but then you realize that if you think about it, this two wave particle has to be one after the other. Because if I look at this one, let's say for example, I continue this transverse wave story. Let me move this a bit here. We know that a wavelength is from this crest to this crest. The first, so I'm going to label them, crest number 1 to crest number 2. But of course, if I draw the wave a bit more, maybe let's say here, there's also a crest number 3. So if I say the distance between two crests is not from crest number 1 to crest number 3, it has to be between 1 to 2 or 2 to 3, which means if you write something like this, where you say that it is the distance between two wave particles, that are in phase, you are missing a keyword. And the keyword here that I will include in red is consecutive. These two wave particles are next to each other. Okay, distance between two consecutive wave particles that are in phase. Okay, or they are moving in phase. So what in phase means, as mentioned just now, is when they move together in synchrony. So what that looks like is go up together, go down together. You can rewind and watch the animation again. Okay, so these are two different distances that we can measure. We can measure the amplitude of the wave, which is how high the wave is, or the length of the wave, which is known as wavelength. So it's between two wave particles that are moving together. And actually what that looks like is just where the wave repeats itself again. Okay, so for example, you can see that this is one wavelength, and then the wave will repeat again at this section here. Okay, let me change color. So here to here is another wavelength. So what we're looking for is repeated pattern. Okay, let's say you want to time a wave. So I'm going to play the wave again for you to see. And there are a few things that we can time. All right, so we could always do what we are used to doing. We can identify a particle. Okay, let's say this is a particle, and we could time by just looking at this particle. Now, if you observe this particle is going to move up, move down, move up, move down. So this looks like an oscillating, movement, and we can measure the time taken for it to travel up to 1. So look at it, it was going to reach 1, and then travel down to -1 before traveling up again. So we are measuring the time taken for the particle to complete one single oscillation. All right. So basically for the particle to return to the original position. Okay. So that could be the first thing that we can time. And the second thing that we can time is actually the wave shape itself. Do you notice that it is traveling from the left to the right? Okay. So let me pause this first. And I'm going to move my particle so that it's at the x is equal to 0 point. Okay, and I'm going to create a reference line. Okay, so now I want you to observe that if I draw a reference line, hey, where's my reference line? There it is. Okay, so I'm going to play this again, and I want you to observe the oscillation and the line. Okay, so as the particle moves down, go up, and return to the original position again. Let's say somewhere here. The distance traveled by this wave is one wavelength. Okay, so you can watch it again. But basically for the particle to travel one complete oscillation, which is down, up, and down again, this reference line will have shifted one wavelength. Two ways to time. We can look at the particle, or we can look at the shape shifting from left to right. So the time that we measured just now is also known as period, and it will be given a symbol t. And because it's time taken, so the unit is second. Alright, so there are two ways to define this. I'm going to label them. The first way is to look at one single particle and measure its time taken for one complete oscillation. So maybe if you start from the middle point, it will go up, come down, return to the middle point again. That would be one oscillation. So that would be time taken. Please be specific. So mention that we are looking at a wave particle or a point on the wave. So time taken for a wave particle to complete one oscillation. Alright, so this is us looking at one particle. But the second way to look at it is to look at the shape of the wave. So while that one particle was moving up and down in one complete cycle, the entire wave has shifted from left to right. Okay, we can replay it and look at the reference line. So this will also be time taken. But now we're looking at the wave shape or the wave profile. So you can say time taken for a, for a wave profile or maybe a crest or wave profile to travel one wavelength horizontally. Alright, so right now, if you think about the simulation, the wave profile has shifted, or we can take the shape, let's say a reference point like crest. So for the crest to travel one wavelength. So just for you to observe the crest, I have indicated the crest here. Alright, and then if we play this, if the particle travels one oscillation, the crest will have traveled one wavelength. Okay. So in this case, a lot of times you may need to look at the simulation or click on the link to try it out yourself. So since we have measured the time and also the length, maybe we can put these two together to measure how fast this pink color wave shape is moving. Okay, so I'm going to play now, and then we are just going to consider again the particle moving one period. So going up and then returning to the initial position. So I'll pause somewhere here. So the distance traveled by this wave shape is from zero origin, because that was where the reference line is, all the way until one wavelength. So by the time it takes the particle to oscillate one complete cycle, the wave have shifted one lambda. Let's put that together in our speed equation. Remember, we are talking about the speed of this pink color shape. So wave speed, because this is speed, we're going to use the symbol v. Okay, and the unit here, speed right? So that would be meter per second. Okay, so this is the speed, wave speed of the wave profile. How fast is this thing traveling? Okay, so if we think about the definition of speed, v is known as distance over time. So the distance that we're taking is the distance traveled by the wave. In this case, it will be one entire wavelength lambda. And the time taken for that wave shape to travel one wavelength would be the period t. So v can be calculated or using the measurements of the length of the wave, and then you time the time taken for the particle to oscillate one cycle. Okay, so this is an equation to calculate the wave speed. And you may be thinking, there's another thing that we can consider, which is the pitch or the frequency of the wave. Now, the reason why we have two different physical quantities to measure time is because sometimes we really do want to know what's the time taken for the wave particle to complete one oscillation. Okay, but sometimes we want to know in 1 second actually how many oscillation is in 1 second. And the reason why we want this, and it's very useful for sound wave, because it gives us information about the pitch of sound. All right, but regardless, the unit for this one would be hertz, short form Hz. Okay, or base SI unit will be S-1. So this is defined as the number of complete oscillations of a wave particle in 1 second. And because it's a number of complete oscillation in 1 second, I can just take 1 divide by t. Okay, so t is the time taken for a complete oscillation, and frequency is the number of complete oscillation per second. That's why it can be calculated by 1 over t. Alright, so since f is equal to 1 over t, I can also introduce it here, right? F is 1 over t, and my v can be equal to f lambda. Alright, notice that 1 over t is substituted with f. Okay, this t, maybe I'll change color. This t, 1 over t, that's why it's at the denominator, is substituted by f. So Vf lambda sometimes is known as the wave equation, but later on, if you study more physics in university, this ain't the wave equation, okay? But this is the wave speed equation, okay? And remember again, this is the speed of wave profile, not the speed of the particle. And now you might be thinking, but miss, what about the particle? The particle is moving, right? And then I'll say, yes, the particle is moving. So the wave particle speed, the actual equation is in A2. Okay, the equation for your wave particle speed is in A2. Okay, but what you need to know for your AS, the thing that you need to know for your AS is actually is there any important points where we can tell the speed of the wave particle? So let us look at a simulation to help us. But remember, you need to be able to visualize this on your own during the exam. So we are here again, and I'm going to move the particle so it's roughly here. And I want you to observe the speed of the particle. You realize the particle is moving the fastest in the middle, represented by the length of the arrow, slows down and stop, and then moves the fastest in the middle again, slows down and stop. So the particle is actually changing its speed and changing its direction or velocity. So this one, A2 stuff, but we can say that the particle is stationary for a short while at the amplitude. Stop for a while to change direction. Slow down, stop to change direction. And it is the fastest at the middle here. Okay, let's note that down. So right now, the important points that we can tell is V equal to 0 or temporary stationary, not moving, at those maximum points when the wave particle is at the maximum displacement. Okay, another useful visual for this is actually for you to think about like a spring. Okay, so as a spring oscillates up and down, the spring or the mass that you hang on the spring will temporarily be stationary at the highest and at the lowest point. So when the particle is at maximum displacement, all right, and velocity is maximum, where is the spring the fastest? Right in the middle, when the wave particle is at the equilibrium position, right in the middle. So when wave particle is at equilibrium position. Okay, so this chapter requires you to actually really understand in your core how a wave moves and the stuff that we can measure around it. Because if you look at the objective question, it can be quite tricky because we are not in Hogwarts and the pictures, they don't move. Okay, so it's your big brain, it's the processor in your brain that will help you move the picture. All right, so what have we done now? In this video, we have looked at how to define all these key definitions, okay, which is important, not just for your paper 2, but also to set you up so that you can use your OP skills to study different wave phenomena. That's it for this video. Be sure you know the definitions, you know how to write them, you know how to measure them, you know how to draw arrows to label them if given a picture, regardless whether it's transverse or longitudinal. I'll see you in the next one. Bye-bye now.